Okay, again, our topic for today will be like an extension of last week's topic. So we will deal with the skin effect, which you probably already know what it is. Then we'll discuss the coupling of the magnetics with the heat, PDE, in more detail than we did last time. And I will also show you two application examples of induction heating simulation. So actual application where you can use magnetics heat coupling. Okay, let's start. I guess every one of you knows what eddy currents are, so I won't go into too much detail. You all know if you have time varying magnetic fields and electrically conducting bodies, there will be eddy currents, and you can maybe explain them by the rule of Lenz. So I won't do this since you're already aware of that and what that is. And the critical part in induction heating is the skin depth and the skin penetration depth. So that's the topic we'll be dealing with in the first half, let's say, of this lecture. So the question is, how can we approximate the skin penetration depth, and what is this skin depth, penetration depth? And this is very important, especially for if you want to heat very thin structures, for example, some thin steel sheets. It is crucial that you approximate, or that you perform an approximate calculation or approximation how deep your eddy currents will, or Joule losses will penetrate the material. So how deep it will penetrate the material, so that for thin sheets, such that the eddy currents don't cancel each other out, which means you don't have any J in E terms, or decrease of J in E terms, so less Joule losses, and this means less right-hand side in your heat PD, so less dissipation and less heat sources. So that's not working that well. So you really want to make sure that your eddy currents don't cancel each other out. Okay, let's perform an derivation of how to approximate this skin penetration depth, and we'll do that by assuming an infinitely half plane, an infinite half plane. So it's infinite in all directions, and here at z equals 0 there's a boundary. So here we have some conducting material where a J, like an magnetic field B or H is prescribed, or an E field is prescribed, and we want to approximate how the fields are evolving in depth direction. So how in this example we'll perform it for the magnetic field strength, how this field strength is evolving in depth direction. Okay, and what's the starting point? Of course, Ampere's law and Faraday's law, as written down here, where we neglect the time derivatives of the displacement current densities, so low frequency approximation, and we also have our well-known constitutive relations. So J is electric conductivity times E, and E is mu times H. Okay, now the question is, how can we deal with this problem, or with these equations in this infinite half plane, or infinitely extended half plane? So let's first investigate what happens to this curl operator in this infinite half plane, and we'll do this again on the tablet here on the right. So how does this curl operator act on this infinite half-plane? So that's nothing new. Curl operator of H can be written as dx dy dz cross product with the components of the vector, and this is simply first write dy hz minus dz hy dx hz plus dz hx, and last row dx hy minus dy hx. Okay, so now let's observe if we have any variations in spatial direction of y. So if you look to the left, this is an infinitely extended half-plane, so there are only variations of our quantities in z direction. So all partial derivatives with respect to x and y are neglected, or there is simply 0. So let's cross them out. This is 0, the x is 0, or neglected, and this one is neglected. So what's the right hand side of this equation? Here we have, if we neglect the time derivative of displacement current density, only the current density, which is again a vector jx, jy, jz, and we assume this j is a j of x, then we can write down the equation that's remaining. So we have the z derivative of hy, and this is our curl equation. So curl h is j in this infinite half-plane. The next equation follows analogously. So we have the curl of the electric field strength again. Write it down, yz minus dx okay, and the right hand side, so d over dt, so the time derivative dx dy dz, and again bx and bz are 0, so the only remaining part is the y component, so minus time derivative of by, and the equation that follows is the z derivative of ey is minus dby over dt, so the time derivative. Okay. So now what happens if we, let's call this our equation 1, this is equation 2. Now let's take another z derivative of equation 1. So equation 1, we take a derivative with respect to z, then we have the second spatial derivative, so minus d squared hy over dz squared is partial derivative of x component of the current density over the Z. Now let's introduce the Constitutive Law. So Jx is electric conductivity gamma times Ex, and we end up with, let's assume we have no spatial dependence of gamma, so we can pull it in front of the derivative, and we're left with the Z derivative of Ex. Okay, and from Faraday's law, we know that this is minus dy over dt. Okay. Then if we write it down again, we have the second Z derivative of hy equal to, again use the constitutive law, B is mu hy gamma mu Z derivative of hz, or time derivative of hz. Hy. Okay, and this equation should be very familiar to you. So we have a second spatial derivative and one temporal derivative, and this is simply so-called diffusion equation. So this is the equation we have to investigate further, and I've already prepared that on the slides. So this is again the Ampere's and Faraday's law in this infinite half plane, and here is the final diffusion equation that I've derived, that we will be considering. Okay, so this describes or models actually the diffusion of the electromagnetic field or electromagnetic energy in the conductor, electric conductor. Okay, and the way we deal with this problem is we transform this time-dependent problem into frequency domain, so into the time harmonic case with this ansatz, classical exponential ansatz. We insert it into our PD, so we have it in the time harmonic case, in a harmonic space, J omega, time derivative, gamma mu times hy, and spatial derivative stays the same, acting on this complex amplitude, and we can identify the characteristic equation of this, let's call it complex diffusion equation, which is simply lambda squared is J omega gamma mu. So we have two roots of this characteristic polynomial plus minus square root J omega gamma mu. Okay, now the general solution, just the solution of this second order ODE, is we have two fundamental solutions. So first fundamental solution is e to the power of the plus branch, and the second one e to the power of minus this square root. So we have two branches, two fundamental solutions, and the general solution is the simple addition of both fundamental solutions scaled with some constants. Okay, so this is the general solution, and we can now use physics to eliminate this first term. So if you imagine e to the power of positive J omega gamma mu z means that our field would be increasing if we if we go into z direction. So this means if we go back to this infinite half plane, the first term would mean that our field is increasing the deeper we go into the material, which is not the case. The physics tells us that the fields are decaying in z direction, so we set C1 to 0, simply based on physical argumentation, and we're on the left with this second term here with e to the power of minus this square root term. Then we just use, we rewrite the square root of the imaginary unit as j, insert it into the exponent, and end up with this equation. So we split up the addition into a multiplication of two exponential functions. Then we can apply a boundary condition. So we assume that our field is 0. Is not 0, at location set 0 has a certain value h0. So we can identify this variable or constant c2 with h0, because if we set this set to 0, this is 1, or both are 1, and c2 can simply be evaluated as h0. So we insert this constant into our general solution, and this is it basically. The only thing left to do actually is to insert this amplitude solution into the full time harmonic ansatz, and we rewrite the square root of omega gamma mu over 2 as 1 over the square root of pf. So the 2 in the denominator is cancelled out with 2 pi f, which is the angular frequency. So this works, and this parameter is called gamma delta. This is delta. So the solution is the initial solution at z0 times e to the power of minus z over this parameter delta. And this delta parameter is now our kind of, we identify it or define it as the skin depth, the penetration depth. So this delta here, evaluated as 1 over square root p f gamma mu, can be identified as our skin penetration depth. So this basically means that if we are at a set direction of delta, our remaining field quantity is a certain percentage, which follows by this exponential function. Okay, so we take the real value of this quantity, and that's it. So we have our derivation, how the field in y direction, in z direction, the h field in y direction looks like if we continue in depth direction of the sheet. So it's a decreasing function. It's an e to the power of minus something, and scaled with this cosine expression that follows from Euler's formula. And this basically means that we have exponential decay of our electromagnetic quantities, and also a phase shift of the quantities. And especially true if we consider eddy currents, which are always forming closed loops. So the loops on the surface, if you consider them flowing at the surface in one direction, they have to close, of course. So they're changing their phase. So at a certain depth set, they're pointing in the opposite direction than at the surface. Okay, and you can also perform this derivation for the magnetic flux density, current density, and the E field. Okay, so it's not some kind, it is actually a boundary layer problem, and this imposes some kind of difficulty when you want to perform the meshing procedure. So if you want to maybe simulate induction heating of a very thin sheet, you need, first of all, high frequencies in order for the eddy current not to cancel out. So that's your physical requirement, the high frequency. And then your numerical requirement is, or can be identified as, a well-resolved boundary layer of your eddy currents. So towards the surface, you need to increase your mesh refinement. Or, of course, so that's an H refinement. If you increase the number of elements, if you're going towards your boundary, that's one way, H refinement. Or you can also use higher order elements. Then you also have more degrees of freedom corresponding to a better resolved field quantity in depth direction. So that's a point you definitely have to consider, and I will also show you the mesh of a real application example in a few minutes. Okay, so the next part we'll be dealing with is how to actually couple the solution of the magnetic problem with the heat PD. And as I've already told you last time, we're doing this coupling via the so-called Joule losses, so this J in E term. So we're actually solving first the electromagnetic problem, given here with this eddy current, classical eddy current problem in pure A formulation, and we want to couple it with this heat PD. So actually that's not a classical heat PD, which would only consist of this kind of Laplacian term and the time derivative term. It's also including a convective term, so that's a convective heat PD, if you want to call it like that. So we can also include some moving objects to be heated in our formulation. Okay, and this QD is the heat source density. So it's actually a dissipative quantity, and this dissipative quantity is transferred to temperature, to heat, via this term J in E. So if we insert the magnetic vector potential into our E field, multiply the E field with gamma to obtain J, and multiply these two terms, we get the representation of the Joule losses in time domain. So we have the time derivative of A in time derivative of A scaled with electric conductivity. So these are the Joule losses, and the question that arises now is, what do you actually want to simulate? That's especially cumbersome if you consider the timescale differences between your electromagnetic problem and the time constants in the temperature problem. So if you have some very thin, I don't know what kind of application that is, some very thin layers that you want to heat up, I simply call it microseconds heating. So if you want to heat up very thin objects, maybe these objects heat up with time constants that are in your limit of in the range of your electromagnetic problem, which is unusual, but maybe there are some materials that behave that way. So in that case, you really need to consider these Joule losses in time-dependent domains, or in this form here, and apply this term, this QD, onto the heat problem and solve the heat problem also in time domain. So solve the convective heat PDE in a transient simulation. So if you have to discretize it in certain time steps and solve this PDE for every time step, and also take care that you're using a good time integration scheme, because this convective term might introduce some numerical issues, as we've already discussed last time. So this is the microsecond heating, Joule losses in time domain, and convective heat PDE in time domain. If you consider like the classical heating process, where you have electromagnetic fields, maybe let's say in the 10 to 100 kilohertz range, and time constants of your object to be heated in, I don't know, in the seconds or 10 seconds range, so you have severe time scale differences. The first ansatz with the Joule losses in time domain and the heat PD in time domain does not make any sense, since there are so many iterations you have to, or so many time steps you have to solve, which are simply unnecessary, because nothing changes in the heat PDE, and you have a periodic solution already in your electromagnetic field problem. So this does not make any sense. So we consider this for the classical simulation heating process. We consider this term here in the frequency domain, so in a period averaged manner, denoted here with this QD overline. So period average, and how we period average this term in frequency domain, I will show you in a few minutes. And the last state or last type of simulation you can use is the steady state heat solution. So if you're not interested in the way your material heats up, so if you're only interested in the temperature your material has at time infinity, so if you consider this setup here and simulate it for an infinitely long time, you get this solution. But this is not always feasible, since who wants to simulate forever? So we want to know the steady state solution of this construct right away. We're not interested in transient effects. Maybe you're not interested in transient effects. So we're also considering the heat PD in steady state domain. So we're neglecting, or we're letting t go to infinity. So this time derivative term vanishes, and we are left with this Laplace term, the convective term, and the Joule losses as the right-hand side. Okay, and the question we'll be answering now is how to obtain these period average Joule losses after or coming from a multi-harmonic electromagnetic simulation. So what a multi-harmonic, or how a multi-harmonic electromagnetic simulation with harmonic balancing is actually set up and derived and solved, we've discussed in last week's lecture. So today we'll simply be converting this time domain Joule losses into frequency domain and perform a period averaging on the fly. So we simply transform, or we insert actually the multi-harmonic ansatz, so a Fourier series from minus n to n for the magnetic vector potential. So we have a multiplication of these two Fourier series, truncated Fourier series, and the period averaging is done by integrating this term over one period and averaging over the period length. We can also transform this into frequency domain, or we can how do we obtain this value, which is the QD over line over bar. How can we obtain this result with the solution of the multi-harmonic problem? So these AK hat and AL hat, these are the solutions of our multi-harmonic system. So the solution of the magnetic vector potential in the different harmonics. And this is done by simply looking at this construct here. So we have an exponential function with j k plus L omega t, and this integral is only non-zero if we're integrating over one period, if k plus L is 0. So we're only interested in the only remaining part is the DC component, the Gleichanteil in Deutsch, of the Joule losses. Okay, so we insert this into the formula, and simply see that we end up with a multiplication of two conjugate complex quantities, because these a k and a minus k, they are conjugate complex. So the final formula for the Joule losses coming from a multi-harmonic solution of the electromagnetic problem is given here. So these are period averaged Joule losses, and these are our right hand side in the heat PDE. Okay, then we already are coming to the application examples. Okay, so our first application example that we'll be considering is this very simple shape of an transversal inductor. So the inductor carrying an alternating current is winded on top of the sheet. So this is actually a half model. The other side, it's simply mirrored, and I've already explained last time, this transversal setup simply means the resulting B field is perpendicular to the sheet surface, and this results in eddy currents kind of in the shape of the inductor. So simply think of this setup as mirrored. You also imagine the second part, and then the eddy currents are simply shaped, have a similar shape as the inductor, so they're in plane of the sheet. And the skin depth can be approximated with 0.7 millimeter. So the sheet itself was 1 millimeter, so not the best setup. So if this was an actual application that was built, I would say let's increase the frequency as such that the skin penetration depth is, I don't know, 0.2 or yeah, not very larger than 0.2, 0.3. Yeah, but maybe you're restricted because these inductors need some powers, especially if the sheets are moving at a higher velocity, and you want to heat up the sheet in a very short time period, from, I don't know, room temperature to 400, 500 degrees centigrade. So you need quite high powers, and for higher powers that are typically needed in these induction heating setups, it is fairly difficult to get some generators that can provide this power at, I don't know, 10 or 12 kilohertz. And then it also depends on the kind of resonator circuit you're using, and typically you have certain types, or I don't know, 3 types of frequency generators available, and you need to design your capacitor bank to this particular application, so that your resonant circuit with the inductor, so this has to be included into your into the design of the whole setup, acts at a certain frequency. And also in real applications, this frequency changes slightly. So if you start with, I don't know, 10 kilohertz or 5 kilohertz and heat up the material, especially if it goes into saturation, the sheet, it also couples back into your electrical circuit. So this frequency that was initially set might deviate. So we had an application where we were adjusting it in the beginning to 10 kilohertz, and after a few minutes we had 10.5 kilohertz. So this is some kind of gray area that is actually following as a consequence of the different material parameters of the temperature. So temperature dependent permeability and also electrical conductivity, whereas electrical conductivity has a little bit minor influence than the permeability, but they do couple back into your electrical circuit. And this is especially true, not that much for these thin steel sheets. It is way more dominant if you have some, I don't know, thick axle or crankshaft, so some solid piece of steel, and if your inductor is wound around the piece to be heated, around the solid workpiece, then you have some massive dynamics going on, and this workpiece then couples back into your electrical circuit much more severely than this thin sheet does. So this also has to be taken into consideration if you want to design the whole setup. So not only the inductor, but you also have to include the frequency generator, the resonance circuit, the capacitor bank, and this all plays together, which sometimes has to be considered in simulation if it's a special application with very precise temperature limits. But typically for, I don't know, industrial applications, there are empirical formulas, or there are specialists that deal with those inductor designs for their whole lifetime or professional career, so they know which capacities are needed to, I don't know, get this kind of frequency. Yeah, so there's a lot of empirical knowledge also in the field of this induction heating here. Okay. Yeah, the kind of pH curve that we were using in this setup here was the let's call it wrong pH curve, since this is the commutation curve, as you can see or identify by this kink here at low frequency, at low field strengths, which is the Rayleigh region that I've discussed last time. So this was not the correct material model for the application. So the better model would have been an anisotropy curve, or ideal pH curve that does not show this kink here in the Rayleigh region. You will see the effects of this kink once again on the next slide. Before that, here you can see the well, don't really see it that well, but you can imagine the green area here is the sheet, and it is discretized with, I don't know, in this case I think it were like 20 elements in thickness direction, and they're also refined towards both boundaries. Yeah. So it was not simply a uniform discretization with 20 elements, but they were also getting denser towards the surface to resolve the eddy currents very well. The problem is, once you have meshed your sheet in that fine manner, the eddy currents are resolved perfectly, but the computation times are increasing drastically, especially if you also want to mesh the surrounding air in this fine manner. And most of the times these inductors are a bit more complexly shaped, as I've shown you in this first application example. So to mesh the air volume with nicely structured hexahedrals is a tedious task, and no one really wants to do, because it's not the nicest thing to do. You have to split up your volumes into some let's call it macro elements, such that the hexahedral meshing algorithm can handle this macro elements and insert hexahedral mesh elements into these macro elements. So the way to go actually is, we want to mesh our sheet, which is rectangular. We want to mesh it with structured hexahedrals. That's a no-brainer. That works out of the box, because it's a hexahedral anyway. And we want to mesh the surrounding air with an unstructured tetrahedral mesher, as it is shown here. So the air, which is kind of complexly shaped because it has a hole where the inductor is placed, this air is meshed with unstructured tetrahedral mesh. And in order to avoid pyramidal elements, so you need pyramid elements to transform from, or to connect hexahedrons and tetrahedrons, because hexahedrons at each surface they have 4 nodes. Tetrahedrons on each surface they have 3 nodes. So how do you connect these two element types? Yeah, via pyramid elements that have 4 node faces and 3 node faces. But these pyramid elements they have some bad numerical features, so they're not very pleasant to use in numerical electromagnetic simulations, because they result in some ill conditioning of your final system matrix. So we don't want to use pyramid elements, so we want to connect hexahedrals and tetrahedrons right away, and we do this by employing so-called non-conforming interfaces. You will hear about the theory of non-conforming interfaces later on in this lecture series, more towards the end. So this is just a remark that we can actually kind of glue these two elements together via some special ansatz functions. So it's actually based on well, one way to deal with these non-conforming interfaces is to use a discontinuous Galerkin formulation just on this interface. But you will, as I've said, you'll hear more about non-conforming interfaces later on. And another advantage of these type of interfaces is that you can also introduce some size jumps. So if you, let's zoom in again. So you see here, at the characteristic length of this grayish tetrahedron here, it has the size of, I don't know, 1, 2, maybe hexahedral elements in length direction. So you can introduce jumps in the element size over these interfaces, and it's a very neat feature, especially if you're dealing with conducting elements submerged in an air volume. So you want to refine eddy currents very finely in these conducting bodies, and in the air domain you don't need the fine mesh anymore, so you introduce this jump, and it's fine. You have numerical efficiency because you're decreasing the number of degrees of freedom of your whole system matrix, and you're increasing the performance. The solver is solving this problem faster than with more DUFs. Okay, here we can again see the effect of, sorry, was there a question? No. Yes. Yep. Okay, so here you see the effect of the kind of wrong choice of the H curve, so the commutation curve, and in this dashed green color graph, this is the nonlinear transient solution, so the kind of reference solution that was obtained with a nonlinear transient time stepping scheme, and that's the curve we want to obtain with our multi-harmonic ansatz. And here you can see that it's not very well represented. We have some even if we consider n equals 5, so 5 harmonics, we still have some major oscillations here, mainly due to the Rayleigh region here, which is increasing the number of needed harmonics, or number of considered harmonics. So that's the downside of this commutation curve, and leading to such oscillations in your solutions. So this was the B field in a particular location. I think it was directly beneath the inductor. I think it was not beneath the inductor. It was at the half plane. So in the middle of the sheet, where this B was evaluated on the top surface of the sheet. Okay, but we can see that we are converging towards the transient, towards nonlinear transient kind of reference solution if we are looking at the Joule losses. So the total Joule losses are depicted here in this center column, and the relative error compared to the nonlinear transient solution is decreasing, although we have some severe oscillations here in this, if we plot the B over T over the time. Okay, so from a theoretical point of view, I would not say that this is a nice solution. It works for maybe an industrial application, but because it is still faster than the transient simulation that I've carried out, the error is decreasing, but we are not resolving the B field adequately, because these oscillations they're not very nice. So in the second application example, which was a real industrial application, we were simulating hollow inductors, because usually they're water cooled, so they're hollow, and also the electrical conductivity of these copper inductors is crucial, since you have eddy currents in your inductor, also due to the back coupling from the sheet into your inductor. So it's not very very visible here in this current density sketch or field plot, which is just depicting a cross section, but maybe you can see some slightly higher current densities at the bottom part of the inductor cross section, because here is the sheet, so the sheet is beneath these three cross sections. And here again we're using a hexahedral mesh in the sheet, depicted here in brown, and also some air volume beneath the sheet, which can be meshed quite in a coarse fashion, since we don't want to resolve anything beneath the sheet, but we need to resolve it a little bit finer on top of the sheet, so pointing towards the inductors, where we have one layer of air. This gray hexahedral region here is another air layer. Then we're imposing the non-conforming interface and coupled to the air tetrahedral elements. The reason I've also tried this example where the non-conforming interface was between the conducting sheet and the non-conducting air domain, and the results stayed the same. So it does not really matter where you impose the interface, if you have an air-air interface or a conducting non-conducting interface. We've also performed some convergence studies, especially dealing with this kind of non-conforming interfaces for electromagnetic simulations, so for simulations where you use edge elements. But you will hear about this later on. Okay, so this sheet here is moving, so it has a certain velocity u. So it enters our control volume with room temperature, so maybe let's say 20 degrees centigrade. Then there comes the inductor, heating it up to, so the first three passes of this inductor heated up to, I don't know, 100 degrees centigrade. Then it cools down a little bit, or it does not heat up that much as directly under the inductor. And then there comes the second kind of boost to obtain the final temperature. Then after the inductor, the temperature of the sheet is cooling down again, and this is depicted in this graph here. So so the x-coordinate is the sheet longitudinal coordinate. So this coordinate here in the moving direction of the sheet, we enter with 20 degrees centigrade. Then there comes the first three passes of the inductor, heating it up to, I don't know, 150, 160, and then the second pass, heating it up to the final temperature. Then the sources, the dissipative sources, so the right-hand sides of your heat equation, do not dominate the heat transfer boundary condition. So the amount of energy you put into is less than the amount of energy going out of your control volume via heat transfer. So the sheet is cooling down, which is obvious, yeah. And here I've compared the solutions for three different numbers of considered harmonics, so 1, 3, and 5, and also the linear harmonic simulation, where you simply take the initial gradient of the BH curve as your material value. So for in the linear case, we see slightly lower temperatures, so the eddy currents are not that high as if you include, I don't know, 3 or 5 harmonics, but the deviation in general is not that severe. Yeah. So the again, from the practical point of view, the temperature difference between 200, let's say 270 and 290 is within the range, fairly within the range of deviations of your industrial setup, because the crucial point is to estimate the heat transfer coefficient or heat transfer boundary condition correctly. So if you have some convection going on, if someone opens the door and air is streaming into your facility, then the heat transfer coefficient is totally different than the one you simulated, and it's off by far more than these deviations you see here. So this is actually the critical parameter in practical application. If we stick to the theoretical point of view, then we do see some deviations for higher harmonics, or for a higher number of considered harmonics. So if we consider the multi-harmonic ansatz with n equals 1, which is, take care, it's not a linear harmonic ansatz, because we're using harmonic balancing to adapt our material parameters, then we are already increasing the temperature. So this orange line here is, orange graph here is the temperature for n equals 1. Then we see another increase of temperature when we consider 3 harmonics instead of 1. But if we go to the next level and consider 5 harmonics, we don't see much difference in the temperature, because with 3 harmonics we're already approximating the whole the nonlinearity sufficiently. So this is true for induction heating processes of these thin steel sheets. If you have some massive workpieces you want to heat up, or as Niels mentioned, if you have some complexly shaped input signal, then you need to increase the number of considered harmonics in your Fourier series. Okay, so with this model you can also perform some efficiency studies. So you can evaluate the efficiency, that eta. Here it is defined as the Joule-loss power over the active power, and you can find an optimal working point over your frequency range. So in this case, the optimal working point was somewhere here at, I don't know, 9.8 kilohertz. Okay, so this is it from my side. Do you have any questions?